So, as my esteemed colleague already mentioned, we will start with the fact that how exactly, in the era of AI, how exactly we can make our models, approaches intelligent when we come to very close to mimicking the human brain. So, all right. So, starting from a very existential question, which is, uh, what is the stark difference between human brain and machine? Human essentially have an innate ability to infer the previously learned knowledge, context, information, and they can use it in the right moment when required. However, machine lacks that. So when we talk about augmenting knowledge and making intelligent machines, we suffer from this problem that machines are susceptible to noises. So it is very important to know what kind of knowledge we are injecting, and essentially also to know how to quantify that. Because if we add too much of the knowledge, that would lead to false semantic changes, and eventually that would lead to knowledge noise, which makes your model even go below or like decline the performance, which could be in general could have been better. The other parameter when you inject knowledge is also to take into account what is the suitability of the knowledge. Is that knowledge relevant? How would you decide that? And also devising some optimal methods that could be taken into account as a common practice to inject the knowledge. So all these questions through this presentation, we will try to tackle one by one, and I will try to the best of my capacity, I would like to answer those questions. So far, the existing methods which actually use knowledge in terms of knowledge graphs, if we consider knowledge graph as a source of world knowledge, they use knowledge graph embeddings. But however, there is a deficiency when we use knowledge graph embeddings, because at times when the domain is very critical and complex, by that I mean, let's say healthcare, psychology, where the context is really important and it could lead to disaster if somehow the context is not properly extracted. So especially also when we are dealing with the human life, psychology or mental health, a person going through trauma, understanding the context of the conversation becomes more and more imperative. So knowledge graph embedding do have worked very well in capturing the context of a knowledge graph. However, they lose context when the sequence is different, when the domain is complex. So in this of my work, what exactly I did in order to better capture the context of or the semantics of the given context or the sentence or the conversation, we use triples directly into the input of the input sentences to model them further and to further pass them to our language model. So that is also the problem statement and the goal of this work. So I named this model as a KLM, which is knowledge language model. So it is made artificially intelligent, which is capable of identifying what knowledge could be relevant and how to discard those knowledge which might lead to knowledge noise and further degrade the model performance. So this is my own designed one of the pipeline, which seems to be very plausible through our external experimental observation. So for instance, let's consider we have certain triples. Triples are nothing but the shorter extracted format from the RDF triples. So a basic example could be Rome is capital of Italy. So Rome is the subject, Italy is the object, and the capital is the relation. So what we are trying to do here for a given sentence, we are adding knowledge by means of triples directly associating to the input sentences. Then it might happen the triples have different variation. So When I talk about Rome is capital of Italy, the subject has only one token. But it could be that the subject length could be 2 tokens, 3 tokens, or more than that. So let's categorize those tokens based on the length of the subject of the triples. So we call it uni, bi, tri, and in general, n triples, depending upon the length of the subject. The reason we will explain further why we have categorized it. And then there is a method that is called forward and reverse injection. So let's see a sentence that says graph embedding representation are the transformation and blah, blah, blah. So in our placeholder, let's say we have some of the embeddings available. So we use embedding that exactly says graph uses human scientific creativity. So this is an input sentence, and there is one word which maps with our list of triples, and we associate that triple to the input sentence. Again, if we look graph embedding, then we have another triple which has a token length of 2, and we associate that triple with another token of our input sentence. And this is how we do semantic enrichment of our text. Now, this is where the uni, bi, or tri subtriple comes in the picture, where we decide if a graph embedding representation will occupy the place and take 1 triple, or graph embedding and representation, they all 3 will take 1 or 2 triples. So that is quantified by iteratively, and there is a parameter called u that decides the number of the triples that will be associated particularly with 1 token. And this model has 2 modules. One is the selection module, and one is the classification module, which is essentially a basic classification model. So the triple selection module take a triple, categorize it, and decide whether the order or the ranking of the triples would be from the increasing order or the decreasing order of the length of the subject. The reason of doing this experiment is that the larger portion of the input sentence mapped to a triple will lead to more precise and more accurate information, because that maps to the larger part of the input sentence. And then another large language model called GP2 comes in the picture that returns us the permeability score that decides out of a given 100 triples with the same subject but with the different objects, which one would be more suitable. So the GPT model, what it takes is that it takes each sentence, check the suitability of each of the triple that is being associated there, and it returns a permeability score, and based on that score, you can decide which triple you want to inject. So it's fully in your control that how you want to decide which triple going to be injected. So here there are 2 methods. One is deterministic and one is non-deterministic. Deterministic is used when the domain is very critical and you want your model to perform really well and understand the peculiarities of that domain. However, one of the challenges of our AI is that we always try to build something which is generalizable, something which can be used for every single domain. So in that case, we do the generalization and we use the approach non-deterministic. So in that case, we don't prioritize our triples. We just inject in the order it comes, and we see the after effect that how it's going to impact our model. The additional feature is that this all injected knowledge in the knowledge layer is merged together and a new sentence is created. That sentence is enriched with triples, and the triples which are added are 1 layer of tree. They cannot go further down like a random forest or something. It's just limited to 1 layer. And that is controlled by a parameter called tree parameter, which you limit to 1. So it doesn't grow iteratively, because then the injected triples would start communicating with each other, and that will lead to false semantic information or false semantic changes. Also, there is a concept of a visible matrix that is governed by the seeing layer that parallelly draws a matrix that prevents the triples branches to communicate with each other in order to mitigate the knowledge noise. So that is in check to mitigate the knowledge noise. So this is how we inject the knowledge, and at the same time, we prevent them from leading to false semantic changes, and then essentially you use it like a transformer model, or you can use any of the large language model or the transformer variants, and you can do the classification. So the strategy that has been developed empirically to inject the knowledge are essentially, as I mentioned, is deterministic and non-deterministic. Deterministic is based on the context. So when we are dealing with a very crucial domain where semantic understanding plays a larger importance, we use deterministic. Otherwise, for the generalization of the model, we use non-deterministic. Then there is a forward and reverse injection. Forward injection essentially prioritize the order of 1 to 3, while the reverse one take into account the larger subject with the larger token. And then we choose whether we just want to send unisubtriple or bisubtriple or trisubtriple. There is, in this entire pipeline, there is a possibility of curating or selecting the things as per experimentally you find more validatory for your particular data set, because there is no one for all solution. Each data set is critical in nature. It could be very unbalanced, and adding something which might not be very relevant or using any world resource as a knowledge base cannot really be relevant or overlap essentially with your data. So you need to put into check that to find that external knowledge, how you're using, is overlapping with your data. So to find the relevance of the knowledge graph, we define another parameter that is called U. That U represents the uniqueness of the knowledge graph. So there might be a possibility that a knowledge graph with a similar subject may have 1,000 triples, but at the end you are going to use 1, 2, or maximum 3. So how do you decide that which one would be useful? So that depends if one of the triple maps your input sentence. If you have a larger database and none of the triple maps your or overlaps with your input sentences, then essentially you are not able to add the knowledge. So this is how you quantify the uniqueness of the knowledge graph, and this is also a validatory check that if you are using a knowledge base, how you can correlate if that knowledge graph or the world knowledge source is useful for your particular data in terms of adding semantic knowledge and contextual enrichment. So to begin with one of the experiment, we use 2 of the knowledge graphs, which is Open University in UK is available, this publicly available knowledge graph developed by one of my mentors. So as you see, there are 2 knowledge graphs. One is the subset and one is in its entirety. So the bigger one having 14 million triples, while the subset has only 12,000 triples. This is the pipeline which I developed. So this is an end-to-end pipeline where starting from the input triples, you take the triples. You can see in the yellow, those triples who are having just 1 token, we call it a unisubtriple. And those which have 2 or 3 yellow color tokens, that represents the subject length of the triple. Those are passed through the triple categorization, and then you process reverse or forward injection. And then you decide how do you want to put this knowledge into the play. It could be reverse or it could be forward. And then you also get to choose whether you want to use it for deterministic or non-deterministic approach that passes through your GPT permeability score. And then finally you send it to the classification module where visible matrix actually kinds of control the interference of communication between 2 branches of the knowledge, injected knowledge. To give an idea, to make it a bit more clear how forward and reverse injection of the triple could work, so let's take into account we have some list of triples. The red one shows that the subject has only 1 length, that is graph. The second triple shows that it has also a length called embedding. The third one shows is graph and embedding. The total number of tokens will be 2. And then graph embedding representation that has token length of 3. Why we restrict to 3? Because then it is very peculiar and very difficult to find a triple which has exact mapping of more than 3 or 4 or 5 tokens and so on to map with just 1 sentence. So that is why we limited our experiment or stopped our experiment until 3, because in based on our experiment, we found that there were very handful of triples and that essentially do not carry a lot of meaning either. So in the forward injection, if graph is given, so then graph, a knowledge triple is added to the token graph of the input sentence, then embedding is added. But in case if we want to do the reverse injection, we will prioritize the triple which has the larger length because that maps with our larger part of the text. So for the entire text graph embedding representation, we just use one triple, that is include a structural and topological feature. These are some of the results from the scholarly domain. The data set was essentially some millions of research paper extracted from the databases existing in public domain, and those papers were used as a paper belonging to artificial intelligence node, so it was essentially a trial check and field testing. So it was a binary classification task. So you can see if we put no order and just send all the triples as they are perceived by the model, the maximum performance is 75. And the max entity is a parameter that controls the number of branching which I mentioned before. So max entity 5 means for a single token in input sentence, let's say graph, we can maximum attach 5 triples to that particular word of the input sentence. So we started from 1, went up to 5, and we tried all the proposed methods and approaches in the pipeline in order to understand what is the impact. So we wanted to have like the entire understanding, what could be the trade-off and which could be the best method. So based on all the experiment analysis, we find that the triple sub-injection has the best performance, and apparently they need only handful of a very few number of triples injection. So for instance, while 12,000 triples were injected in unisub triple or bisub triple, trisub triple were only handful, something around 157, and still they were able to outperform. So the full KG injection is actually the base BERT, and the best performance is 81.98 with the sub-triple injection. So you can see a very stark difference of 5 to 6% of accuracy change with a very simplistic approach. And also, this is computationally light because it is parallelly processed and everything is done independently. So it's not even a matter of a cost. But with just curating and identifying the right source which can lead to a optimal knowledge injection, we can see that we need not to train very large models and use large computational resource. We can really work fine and outperform existing state of the art even with these approaches. So we have field tested in a scholarly domain, healthcare and psychology domain, and now I'm testing it in agriculture domain. So these both were the results with the deterministic and non-deterministic, and of course, for obvious reason, the deterministic approach has always proven to be better because that is more oriented and more relevant to the particular data set which we have been using. So the takeaway could be that the proposed model with any of its methods outperform the existing state-of-the-art in classical machine learning. Apparently, among all of them, sub-triple injection method has proven to be like winner in all situations, regardless it's deterministic or non-deterministic. And as I mentioned, sub-triple injection required far less injection and the process had been really, really fast and simple. There is a paper also if you want to have, it's very comprehensive and like it has put out all the details to implement it. The source code is available in case it's a good read, and if you want to get some idea, you can definitely go there. And that would be all. Thank you.
Thank you so much, Vivek. Let's sit a bit and look at some questions. So sure. Very deep presentation, let me tell you, very interesting. So I have a few questions in the app. The first one is really about examples of domains where the non-deterministic injection is more important than deterministic injection, although the precision is better, as you said, with deterministic injection.
Right. So when we talk about deterministic approaches, it's more pertinent to the domain which are very peculiar. For instance, when we are dealing with the human lives, mental health, psychology, counseling therapy, conversational therapy, and even identify the system through symptoms or diagnosing present, like finding information or extracting information from the electronic health records, it is very important that we understand the fine nuances of that particular domain. And in that case, the domain knowledge definitely comes into play. But in general, if we are playing around to do classification or identifying the sources, and that domain is rich in training data availability, and there is no challenge of the scarce data, the data is very balanced, then you can take the approach of non-deterministic.
Mm-hmm.
That would be more, useful
Sure.
in any case.
You talked about that the data set that you used was an open data set from UK on research papers, right?
Right.
So what other domains from your experience do you see where this methodology is more applicable, where you need to inject more knowledge in those domains?
Okay, so one of the domain where I have been working in very detail was psychology, military psychology, and in general psychology. And I found that apparently there was no publicly available comprehensive data. So this is how the idea came in, because in my mind to first start with developing a data set to generate a resource that could help the further researchers of this community. So with my peers and with my colleagues, we developed a data called NOMI, which is the expert annotated data. And first of its own kind, and it's GDPR compliant and publicly available, and it's the psychology data. So that data was heavily unbalanced. So to mitigate the problems of the bias because of unbalanced data set, and the scarce data because the training data was so less that a deep neural network cannot be trained properly. So this is how this model came into the picture, and we applied over there to mitigate all the biases that was being induced because of the data scarcity.
Okay. What about scalability of this model?
Well, so far we are testing, I think this is the third domain I would be testing this model. So it is very scalable in my understanding, and as I mentioned, that it is computationally very light because everything is processed separately, so it doesn't need really a large computational resource either.